Well, I will try to warm your hearts with the cryptography and cryptology of proxy re-encryption. Give me just another minute. Okay, my name's Justin. I'm with NuCypher. I'm going to give you an overview of how our cryptology is written, how our cryptography works, and then, Wi-Fi permitting, and many other things permitting, we'll have a live demo of our testnet. But first, because the space has such nice acoustics, I think we need to start with a song. Starting with a song always helps the chances of a live demo go from very little to little. Anybody know what that song is from? Nobody played Final Fantasy IX. Phenomenal game, great soundtrack. All right, let's get down to it. I'm going to start with a high level. We're going to dive a little lower. I'm going to walk you through some code that we've written that we think is inspirational and different and meaningful for the decentralized age. The first thing I want to impress upon you is that while we have written a couple of underlying cryptographic primitives that we think are meaningful and important, and I'll go over those, a lot of the challenge for us has been writing an overarching cryptology that these cryptographic primitives might be properly understood within the logic of a decentralized application. My sense is that a lot of you have faced similar challenges, so I want to kind of address how those work and why we think they're meaningful. First, you may be accustomed to the narrative between Alice and Bob, this tense, ongoing 40-year relationship where Alice has a secret that must find its way to Bob. In our cryptology, we've added 2 additional characters to this narrative who we think are essential for decentralized application development. Ursula, the untrusted re-encryption proxy. Ursula takes ciphertexts that are encrypted with one public key and makes them encrypted for a different public key. Typically, we use this logic so that someone can encrypt for a policy, and then Ursula can take the ciphertext, never seeing the plain text, and re-encrypt it so that Bob and only Bob can read that ciphertext. Ursula is the character that we run on our NuCypher networks. We think that she is the character that is worth, she'll stake our token, and we think that her services are worth paying for. Our plan right now is that you'll pay for them in a small amount of ETH. So as a DApp developer, you won't need to consider the NuCypher token. You'll be able to pay for this service in Ether. Another character that we've added to the narrative we call Enrico, the encryptor. Why is it that Alice, the person who decides who gets the message, has to be the same as Enrico, the person who constructs and encrypts the message? Now, in public key cryptography alone, it's true that these two do need to be the same person. But because we've implemented proxy re-encryption in a fairly robust way that is easy to understand and also has a lot of the sort of safeguards that you need in order to use this technology in a decentralized way, we are able to provide separation of these two actors. Now, that might seem strange. It certainly seemed strange to me when I first heard about it. I was like, you can take a ciphertext that's encrypted for one person and re-encrypt it for another person? But indeed, it works. And in fact, reading through the math, reading through our Python, which I invite you to do, you might find that it's simpler than you're imagining. So what I want to do now is invite you to take a little trip with me through some of our Python, and I'll show you the code for the demo that we'll run that shows the basic picture of how our network works. Make sure we get back on here. I almost need to be like down here. First, actually, let me give you a really brief picture of the construction of our code base. Among many other higher order objects in our code base, we have characters. So when I talk about Alice and Bob and Ursula and Enrico, these are not merely concepts or mechanisms for assisting in our documentation. In fact, we have code for these characters that describes exactly how they are permitted to behave. Here's Alice and Bob and Ursula. So if you like, we invite you to read through what we've tried to construct in the form of almost like a screenplay so that these characters might interact with each other. Interestingly, another thing that we've started doing that I think is important for any network that values security is we've begun to define unlawful characters. In this case, we have a character named Vladimir. Vladimir does the wrong thing. He attempts to be Ursula when he's not. And we've characterized the types of attacks that we think are available to Vladimir in a Vladimir character so that it's simple to run either in our test suite or on a network an unlawful character and show that our network is robust against those attacks. So again, we've documented these attacks using an unlawful character. We have different alignments. We haven't introduced the chaotic character yet, like a chaotic neutral character, but that may be coming. All right, let's go through the demo. Here we go. We call this our Finnegan's Wake demo, and we'll run it on the NuCypher testnet. It will fail with a bad connection, so I don't know. It might just fail here. I don't know. I'm going to stand back up. So we just threw up a load balancer for our testnet, which felt like some kind of accomplishment. It's funny, you put up a load balancer for like 70 web applications over the course of your life, and it feels like nothing. But you do one for a decentralized testnet, and you feel like you've added some tiny bit to the corpus of humankind somehow. I don't know. First, we'll show you Ursula, the untrusted re-encryption proxy. Now, it's hard to show you a demo without touching on the way that we do node discovery. Here you can see that we make an Ursula from seed and stake info. Okay, we have our testnet load balancer, which has 10 Ursulas behind it, a directory where we'll save TLS certificates. This demo is going to be federated only, meaning that Ursula won't be staking any token and we won't have to pay. That also means that the network is less trustworthy, of course, but for testing and development purposes, this is substantially less configuration hassle, right? So that's nice. And the minimum stake we require for a given Ursula is 0, again, because this is a federated demo. Here are the details of our policy. Okay, the policy will last 5 days, now plus 5 days. And we have what we call M and N values of 2 and 3. Bob will need to, so the way that this will work is that Alice will fragment a key into pieces that we call K-frags, and she'll make N of those K-frags, in this case 3. Of those, Bob will need to visit 2 Ursulas. Alice will give kfrags to each of 3 Ursulas, Bob will need to visit 2 in order for the service to be properly rendered. These values, of course, are tweakable. Higher values will have effects both on performance and security, and you might choose to tweak them to be consistent with the game theory of your application. It's also possible that consensus will emerge in the community on ideal values for M and N for networks like ours, and that those will simply be the ones that everyone uses. We have a label. We originally conceived of NuCypher as merely a KMS, a key management system. This label is a way to, perhaps a touchstone to help you think about it in key management terms. Imagine that this is a directory that Alice is trying to share with Bob, with many Bobs. There may be many labels, there may be many Bobs. Anybody can put things into this directory, but only the Bobs that Alice specifies can decrypt what's in there. Okay, here's Alice, the authority of the policy. We give her network middleware. We give her known nodes. Again, she knows about the seed node that we've constructed from our NuCypher testnet. She'll learn on this thread. Normally we have multi-threaded node discovery, but for the purpose of this demo, that's not important enough to add the complexity, but it works. It's built in. Again, it's a federated-only demo, and we also tell Alice where to save certificates. The same details apply to Bob. Here, Alice starts what we call our learning loop. The node discovery. I do want to note that just yesterday we posted a blog post about our learning loop and about why we decided to roll our own node discovery, what we call intraplanetary node discovery, as opposed to the interplanetary node discovery embodied by, for example, libp2p, which is a wonderful project along with IPFS, but didn't fit our node discovery needs. Here, Alice grants on the policy. So this is typical of the sort of NuCypher language. We do alice.grant to Bob. She grants access to the label. Here are the values of M and N that will affect how she engages the network, and here's the policy end date time. Now Bob puts her public key somewhere for Bob to find later, and then disappears from the internet. So here's a situation where Alice can go offline, something we think is perhaps one of the use cases of NuCypher, and yet the policy can continue. Some time passes. How do we make time pass? Many of us grew up on the Ocarina of Time, right? We know how to do this. And then Bob groggily awakes to find himself in the temple of time, surrounded by the blue light of the policy to which he's been granted access. Here we have Bob. Bob the Biddler. Most likely, if you're developing a distributed application, whichever other characters you use, it's quite plausible that you'll use Bob in the logic of your distributed application because, after all, you want access to the data. So now, here Bob joins the policy, right? Fairly simple, similar syntax to grant. Bob joins a policy for a particular label. Let me actually get back into presentation mode here to make it a little easier to read. He joins a policy for a particular label, and in order to do that, he needs to pass in the public key that Alice left behind somewhere on the internet, perhaps IPFS. Now that he's joined the policy, let's show how Enrico the encryptor can share data with members of this policy, and then how Bob retrieves it. Okay, here we load Finnegan's Wake by James Joyce, and we will iterate line by line through Finnegan's Wake. Enrico, using the public key of the policy, I'll pause here and note that, again, Alice generates the public key of the policy, and she decides which Bobs are in and out of the club for that policy. Then, when anybody, such as Enrico, encrypts for that policy, all of the Bobs, and only the Bobs, will be able to decrypt it using their private key. In this case, the message, the plain text, is a simple passage from James Joyce's Finnegan's Wake, You may have heard of this book. It's incredibly cryptic and strange and bizarre, and yet people spend years or decades of their life reading it. We leave the matter of whether encryption makes this passage more or less readable to you. Enrico encapsulates a single message from the plain text. He gets the single passage as a ciphertext and a signature. He leaves behind his public key, and then Enrico can disappear from the internet. Now we go back to Bob. Bob has to reconstruct Enrico in order to verify the signature. Bob wants to know that the message did in fact come from someone that he has a pre-existing relationship. Maybe, maybe not. Maybe in your application, this is a fire hose and anyone can announce to Bob, but we're showing here that this is verifiable. Now Bob can retrieve the original message. He dusts off Alice's key that she has left somewhere, and Bob retrieves. We run bob.retrieve using the single passage ciphertext, the Enrico as Bob reconstructed him, and Alice's key. And now we show that indeed this is the passage originally encrypted by Enrico. Is it going to work? Is it going to run? Obviously, it's partly a matter of network connectivity, but I think it is about time to give it a try. We will run. In here, you might see, assuming it runs at all, and it is, you might see a few red unhandled errors. That's because this node discovery, when a node is unreachable, we just haven't added a nice error message there yet. So that's what you're seeing there. And here you have it: James Joyce's Finnegan's Wake, each line now being re-encrypted by Ursula so that only Bob can open it with his private key. Now, how the heck does this work? This is quite strange, right? The underlying cryptographic component, the cryptographic primitive that allows us to write such a strange cryptology, is called proxy re-encryption. Here we have a graph that explains essentially the minimum logical understanding of proxy re-encryption. Here's Alice. Alice makes a re-key from Alice to Bob, and another re-key from Alice to Charlie. Charlie is not a name that we use in our code base. It's just another Bob for simplicity and documentation. Again, in the NuCypher network, Alice would split these keys up n times, but we don't need to show that on this chart. Here's Ursula, our proxy. Someone can encrypt using the private key of the policy, the public key of the policy, and then Ursula can re-encrypt for Bob and for Charlie because she's in possession of these re-keys. Now this means that, as we already showed, Alice can be offline completely. It also means that via logic that you all determine, the proxy can start the policy at a later date, if that's what you want, or end the policy early. In fact, we are just introducing revoke into our code base. The pull request is open right now, so that Alice can revoke and then tell the proxy, don't re-encrypt for Charlie anymore. It also means that devices need to encrypt only one time in order for a very large audience to decrypt. So you can imagine if you have small devices and you want to just tell them, here's the public key that you're going to encrypt for forever. And then Alice can continue to add and subtract Bobs from the policy, decide who's in and out of the club. That's something that proxy re-encryption and the NuCypher network enables that we're not aware of being available prior to that. You might imagine Alice being a patient and Dr. Bob and Enrico being the medical devices that Alice has. Now, the medical devices don't need to know who Bob is, and vice versa. Alice can decide which Bobs, which medical providers, are in and out of the club for all of her medical devices without ever needing to change the public key that they understand to encrypt for. Switch to guitar. Now, in NuCypher, we think that privacy, access to reasonable cryptographic secure primitives that are well-researched and well-written and easy to understand are a basic human right in the information age. And that doesn't mean that everything in the world needs to be private. For those of us that, who include myself, believe that data in some fundamental natural way wants to be open, this is not a contrary philosophy, but what we provide is the opportunity for data to remain private for a time, to incubate in our groups and in our communities with the safety that it is verifiably away from the larger eyes of the world. And we think that that's an exciting opportunity that comes with decentralized networking. You know, it's very exciting that suddenly Bitcoin seems to have caused this bootstrapping where there is opportunity, there's money available to build cryptography and meaningfully, and that's really very exciting to us and something that we take very seriously. Questions? Do we need to get questions on the microphone, or is that? Go ahead. I'll repeat the question in case it's for the recording. Go ahead. Oh, he says Final Fantasy VII was better. That is a debate that we will have to take outside, Padna. I love Final Fantasy VII also, don't get me wrong. Yeah.
By creating such a system, don't you make Ursula the great point of failure?
What a phenomenal first question. Don't we make Ursula the point of failure? Let me explain to you the precise attack surface represented by the availability of Ursula. If M Ursulas collude and Bob participates by proffering up his private key, that is a grievous attack. That allows that group, again, consisting of M Ursulas and Bob, to produce cryptographic material similar to Alice's private key, which would give them the power to grant on this policy to interlopers. But if you consider the diameter of this surface, you're already involving Bob's private key. In most crypto systems, if Bob's private key is compromised, the game is over anyway. Here, Ursula never sees the plain text, is not trusted by Alice and Bob, and is also needed to cooperate with Bob to achieve the compromise that we're talking about. Of course, Bob can take his own private key and share the original data, but in order for the policy to be compromised, you need M Ursulas to collude along with Bob. So it's a very real phenomenon, and it is a surface that you need to consider in your security paradigm. But Ursula is not trusted. Now, you might imagine that someone might spin up 10,000 Ursulas in an attempt to hoover up M keys, right? That structure, that overlay topology, I'm of course using that term a little bit differently than it's traditionally used, but I think it still makes sense. We prevent that, what is essentially a Sybil attack, by forcing Ursula to stake NuCypher token. So, you know, it's possible that someone will buy up a lot of NuCypher token in an attempt to execute a Sybil attack. We can't say that it's totally impossible. But what we can say is that we have essentially the same robustness against a Sybil attack that blockchains provide against Byzantine faults in the first place. And I want to just reiterate one more time because I think it's very important. M Ursulas together can't really do much. M Ursulas can get together, and all they can do is continue to re-encrypt. They cannot see the plain text. Other questions? Yeah. Is it possible to detect such an attack? We were actually discussing this very matter at, I don't know, after 2 but before 3, I think, last night. I am of the opinion that the safe way to proceed is that the answer is no. That does not mean that we won't build tooling to increase the plausibility. And if this attack ever happens, we would love to catch the attacker red-handed, of course. That would be both, well, mostly fun. I don't know how effectively we would be at chasing them down. Is it possible for Alice to detect this attack? We intend to build tooling that listens carefully to our network and tries to detect the signs of such an attack. But it's not clear to all of us how plausible that is. I mean, consider that in an ordinary public key encryption scheme, is it possible to detect if Bob has given his private key to the NSA? No, it's not. If you consider, or maybe you know what Shamir's secret sharing scheme is, if Ursulas had the secret themselves, if only M colluded like in a Shamir secret sharing scheme, you might imagine that M Ursulas might run to the NSA and attempt to help. In this case, both are required to be on that team in order to compromise that original key for the policy. So we think that it is an advancement in the robustness in terms of resilience against that style of attack. Other questions? What was the adjective? They're quite what?
Like, how did you come up with that? Because also, talking about this look like a figure in the sky, that's it. Like, why Ursula's name speaks about tokens? What about others? And there is also, when it reads NuCypher tokens. How do you come up with the token mechanics?
You know, that's a very big and meaningful discussion. I hope it's okay. The question was, how do we come up with our token mechanics? And this is a phenomenal question, but it also represents, of course, a can of worms. Very exciting, but we do have an economics white paper where I think it's explained better than I could possibly do on the stage. I hope that doesn't feel like a dodge to you, but it's a very difficult a very difficult question to answer. And by the way, we, and I hope all of you, are open to the possibility that what we've outlined for mechanics to create trustworthiness and Byzantine fault tolerance in our network are not going to be right the first time around. We're totally open to this idea that better ideas will come along and that we will implement them, and we're always on the lookout for them. So, of course, feel free to join our Discord and tell us exactly how you feel. Other questions? Is that it? I'll just leave with a little bit of a song. Away from the microphone for one, even though it won't be on the video.